Okay, yeah, hello everybody. I think that we can start. Our today's speaker is Vladimir Podolsky, and the title is Constant Depth Sorting Networks. Vladimir, you're welcome.
Thank you. Yeah. So I have slides, as you can see, because I already had them in advance. So yeah, I will just use them. And but still, I would like to give you ideas of the proofs and things like that. So please ask me anything and interrupt me and so on. I will try to answer questions during the. So okay, just I guess it's clear. Okay, so we will be talking about constant depth sorting networks. Let me just introduce the model right away. What is the sort network is? So we have an input, and the input is just an array of integers. Let's say integers here, and on the output we would like to produce the same array but sorted. And there are some elementary operations that are called comparators. In each comparator, we take a pair of inputs, pair of input numbers, and sort them. And you can see a picture. So here, these vertical things are comparators. So the input is on the left, the output is on the right. So on the right, sorted, as you can see. And I just also would like to stress that sorting is from bottom to top in my picture. So this is the usual picture for sorting network, as you can see in books on sorting networks. But it is usually sorted from top to bottom. For me, it will be convenient to sort from bottom to top. Okay, so on the comparators, it is convenient to organize them in layers. And for example, in the first layer, we have these two comparators. So we sort 2 and 3 and 1 and 4. On the second layer, we have this comparator that sorts 3 and 4, and another comparator that sorts 1 and 2. And on the last layer, it turns out that it's just enough to have this one comparator, and that's it. And the depth of the network is the number of layers. So these are the main definitions. If there are questions here, please ask, because that's kind of the whole talk will be about these things. Okay, if this is clear, then let me just briefly give you some motivation. So it's a simple, so sort network is a simple model for sorting. Of course, it is weaker than general comparison-based algorithms, because in general comparison-based algorithms, you can, okay. I have a fire alarm in my building, but let me just stay here for some time, and maybe if it persists, I will have to leave the building. Okay, but for now I will just stay. Yeah, I will check real quick what happens in the corridor. Okay, people are leaving actually, but let me just give you at least something. So sort network is a simple model. It is weaker than comparison-based algorithms, because in comparison-based algorithm, next comparator, so the next thing we are going to compare might depend on the results of previous comparisons. It is convenient. It was originally studied because it's convenient to implement in hardware, because everything is fixed in advance and you can just lay out this network and that's it. Also, it is convenient for parallelization, because if on each layer, all of your, I think it stopped, great. All of your comparators are on the same layer. If they are all on the same layer, you can actually, so you can see here, you can actually compute them in parallel. So on the first layer, you have two comparators and you can compute them in parallel and so on. So it is convenient for parallelization. And okay. It is an old model and still there are open problems. So I guess this is all kind of clear. If there are questions, please ask. So what is known for the depth of sorting network? So there are many constructions of depth log square. There is odd even sorting network, there is pairwise sorting network, and so on. So there are many of them, and it is not hard to do. Usually, they are based on merge. So so on divide and conquer. So we split an array into halves. We sort both halves separately, recursively, and then we merge them in logarithmic depth, and then it will be enough. I can actually give more details here if you want. And also there is a construction of log depth sorting network. This is a celebrated paper by Aitai-Kobos and Semereti. So there is such a thing. There are some drawbacks to it. So it is complicated. So it is really hard to read. So they actually, for this construction, they use pseudo-random generators, then they randomize things, and it is a complicated result. And also note that there is a convenient big O notation here that is extremely convenient, but in this case, it hides a rather large constant. So actually, no one uses this in practice because for reasonable numbers, Fn is not extremely large, then this construction is still worse than some simple log squared construction. And okay, for the lower bounds, there is a question, I guess. The recording. I think it will be. I suppose it will be available on the website of the lab. So on the site of the lab, you can find the link to the YouTube channel, and then probably the recordings after several days will appear there.
Yeah,
Please
I hope
correct
so.
me if I'm wrong. Yeah. Okay. So for the lower bounds, there is a very simple. It says that it's folklore, but this is just basically it's information theoretic argument. So okay, maybe it's rather easy to explain in the following way. So to sort n numbers in a comparison-based algorithm, it is well known that you need n log n operations and n log n comparators, because there are n factorial permutations, possible permutations, and you can get any permutation of an input on an input, and you have to sort this permutation. And so the outcomes of all comparisons in your algorithm should be okay. If you make k comparisons, then there are totally k outcomes, and it should be at least n log n. So k must be at least it should be at least n factorial, of course. And from that, it's basically n log n comparisons needed. And now note that in each layer where you can fit each layer
n over 2.
Yeah, each layer can fit only n over 2. So this gives you 2 times log n layers. This is an obvious lower bound. And okay, then it was improved a couple of times. So there was a paper by Yao, but currently the best known lower bound is something like 3.27 log n. That's the best what is known. Okay. Yeah, I also should have mentioned that log n lower bound is obvious. So before we even do counting argument, the lower bound of log n is kind of obvious, because if you want to sort things, you need so for each entry of an output, each entry of an output should be connected to all inputs. So log n depth is kind of obvious, even more obvious than 2 log n. Okay. Now, what we will actually do in this talk, we will consider generalization of this model. So we will call it k-sorting networks. And in this model, the generalization is kind of obvious. Now we have, instead of comparators that compare 2 numbers, we can have comparators that compare k numbers, up to k numbers. So the array of comparators now is small k, and k here is a parameter, so we will be interested in k from now on. If k is equal to 2, this is the original model. Now we have arbitrary k. You can see a picture here, and there are some, again, comparators are organized in layers. Each comparator has its own color now. So on the first layer, so here n is equal to 8, k is equal to 4, the depth is equal to 3, the number of layers is 3. So you can see probably, okay, this is the first comparator on the first layer, and this is another comparator on the first layer. So in each comparator, we compare we just sort all of the numbers that we get to this comparator. And you can see that. So in the first comparator, you sort all of these numbers. They are now sorted. Again, I sort from bottom to top for convenience. For you will see in the end of the talk that it is convenient for some reason. On the second layer, there is one comparator that is here, and there is another comparator that is here. And on the last layer, you can see that there is a comparator in the middle, and there is a comparator on the sides. Again, we sort 8 numbers like this. Okay, so we can consider this model, and actually it is not something new. It was studied before, and actually since 70s, and the main motivation is kind of the following. So first of all, it's rather natural. We do not understand completely how sorting networks work. So we might want to study with generalization. Maybe it will help. And still, also, as far as I understand, there is some motivation in terms of practice, maybe. So maybe from practical point of view, if you want to actually implement sorting networks, it might be reasonable to consider K-sort networks. I don't know much about that. And finally, another natural idea is that, okay, maybe if we construct a good sorting network with some K, then we can actually reply it recursively to itself, and then get a good construction of actual of sort network with K equals to, so with K equals to. So basically, if you want to sort in numbers, we can apply sorting network with some K, and now we have inside many comparators working on K numbers. Now we can apply the same construction. So instead of N, we can use K, and we can apply the same construction, and we can repeatedly apply it again and again. And if parameters are good, hopefully we will get a good construction of a sorting network with just K equals 2. Eventually we'll get to K equals 2, and then we probably will get some good construction. That's the idea. Okay, so what about upper and lower bounds? The upper bound here, again, there are log squared upper bounds, and the best one is like this, so the constant is even known, so it's 4. And also there is the goal of log n construction. Yeah, note that here the base of the log is K now. And it is a generalization, so you can actually get it from Itaikov's and semi-ready construction. So, and the only source I know actually is Quattal's lecture notes on this construction. So he explains in lecture notes Itaikov's and semi-ready sorting network, and on the way he's also explaining that you can actually generalize. I do not think it is officially published somewhere, anywhere, but it is online, so you can actually find it online. So, okay, but what we will do in this talk? In this talk, we will study the following. So we will study the following problem. Suppose you want to sort n numbers, and we have K sorters, and we want numbers. We have n, size of array is n, sorters are K sorters, the depth is d. What is the minimal? Suppose we can fix d. So suppose we fix d. What is the minimal K for which this is possible? And basically, the motivation is again for iterative constructions. If we prove a lower bound for K, then we show, if we prove an upper bound for K, good upper bound for K, then we probably get a good construction for sorting networks, and then we will apply them iteratively and get a simple construction for low depth standard sorting network. But this is not what will happen during this talk. Instead, what we will do, we will show that there are lower bounds. We will show that for small d, K must be large. And this rules out simple iterative constructions for low depth sorting network. That's what the plan is. And actually, I could have stated the result that we get right now, but instead, okay, even before that, I would just like to let's just have a short break and discuss one simple thing about sorting networks that will be useful in the rest of the talk. So if we have a sorting network and we want our sorting network to sort any set of integers, how can we check that this is indeed correct? Because the number of possible integers possible inputs is large, and you do not probably want to test all of them. Actually, it turns out that it is enough to test all binary inputs. So if our sorting network sorts numbers, then obviously any integer numbers, then obviously it sorts 0 and 1 inputs, but vice versa. So the opposite is also true. So if our network correctly sorts 0, 1 inputs, then it can sort any integer inputs. This is a well-known thing. This is called 0-1 principle. This is very standard thing, but we will kind of use it in the talk, and probably you can tell me how to prove this. Or I can just give you a proof.
Give us a proof.
Okay. Then the idea is the following. So let's prove this lemma.
If it sorts incorrectly, just make a threshold which placates this incorrect sorting, I guess, yeah?
Yeah. Right. You argue by contradiction. I do this. I will just do the same, but without contradiction. So let's just introduce some threshold. Let the threshold be 2.5 in this case, in the case of this picture. And let's do the following. Let's substitute. Suppose we know that we sort integers, right? Okay, we want to prove it. We sort integers from 1 to 4. Let's substitute each integer that is above threshold by 1 and each integer that is below threshold by 0. And then we can observe that this is a monotone operation, right? So so we will apply minimums and maximums, but the outcomes are still the same. So actually, it turns out that now we have 0, 1 input. And we know that we sort 0, 1 input correctly. So here we will have things like that. And this means that in terms for integers, it means that two larger integers go here and two smaller integers go here. And now you can repeat it for each threshold. And then you know that the largest number is on the top, the second largest is on in the second one, and so on. Does it make sense?
Right. Yeah.
Okay. Okay, cool. Yeah. Now, but okay, before I tell you the results, let me also tell you about some other research that is kind of related. And this is about, so this is actually it's a problem. Let me name some sub-problem of what we are actually studying. And this is about computation of majority by monotone Boolean circuit. So we have a majority function. It receives n Boolean inputs here, and it outputs 1 if the sum of inputs is greater than n over 2. So if most of inputs are equal to 1. And we want to compute this function by a monotone Boolean circuit. So the gates are ands and ors of 2 inputs. And we will, so actually the fan-in of gates, I will use, so I will write in a subscript. So in the subscript, you can see the fan-in of each gate. And we are interested again in the depth of such a circuit. And here is an example of a circuit that computes majority of 3 variables, but probably just if there are questions, but I will explain it. If there are questions on the model, I will explain it in this example. If there are no questions, I move on. Okay, so first of all, I'm saying that this is a sub-problem, right? Why this is a sub-problem? Okay, let's consider inputs in 0, 1, so Boolean inputs. And then we can observe that the majority is just the middle bit of a sorted array. If we take a 0, 1, so arrays of zeros and ones, then the majority is the middle, because if, okay, we have zeros and ones originally, 0, 1, something like that. And then we sort it, and then there are zeros in the beginning, and then there are ones after that. So we can tell now, so it's easy to tell how, so is it true that the number of ones is greater than half or not? So we will just check the middle bit. And if it is 1, then there are more ones there. If it is 0, there are more zeros. So the majority is just a middle bit of a sorted array. So if we sort an array, then we also get a majority. Also note that for Boolean inputs, the operations are AND and OR are just minimum maximum are just AND and OR. So minimum is just AND and maximum is just OR. So actually, if you have a sorted network, you can consider it on 0, 1 inputs. You can substitute each minimum by an AND, each maximum by an OR. Note that recall that each comparator is computation of a minimum and the maximum. And so from sorted network, you get a monotone circuit for majority, because you have now a monotone circuit and the middle output is a majority. And the depth is the same. So given a sorted network, you also get a computation of majority. And okay, what does it mean for our problem for the majority? That we know that there is a sorted network of logarithmic depth. So it gives us a monotone circuit for majority, right, of logarithmic depth. And this is not only a way to prove that there is a lower bound, so there is a logarithmic depth Boolean circuit for majority. Another result, so another proof belongs to Valiant, and the proof is, I will give you a proof idea. So the proof is the following. So let's just consider the following formula. On the top, you have OR, on the next layer, you have ANDs, on the next layer, you have ORs, and so on. And take the depth to be 5.3 logarithm n. And so this is the structure. It is very structured, right? So, but now the main point is how do we assign the inputs? So for each leaf of this tree, we assign a random variable from the input, and then you can actually prove that this circuit. So you can actually prove that with positive probability, this circuit will actually compute the majority function. These are the concentration inequality, so it is not very hard to prove, but okay, just that's the whole idea. Then after that, it's just the techniques. It's not technical computations. It's not complicated. Okay, so now for circuit for majority, we have two constructions actually. So we have two proofs that there is such a circuit of logarithmic depth. There is AKS construction. It is explicit, so you can actually construct the circuit. It is in polynomial time, but it is complicated and it is impractical because the constant is large in front of a logarithm. There is a valid construction, which is really simple. I just explained the construction, but it is not explicit, so it's randomized. Still, there is an open problem, so we still are looking for a simple and practical construction of logarithmic depth circuit. And again, the recent line of research was kind of similar to what I explained for sorting networks. We can consider low depth circuits for majority consisting of majority of k bits, of smaller number of bits. And again, the motivation is to better understand the structure of majority and possibly to use it to get iterative constructions. Okay, so that's what we can consider here as well. And the problem, again, I restated it here. We want to compute majority. The depth is constant. We want, as gates, we want to use majorities of k bits. What is possible? And here, just for the reference, so just so visualization of model for depth equal to. It looks like that. Okay, so these are some results. The first results here were obtained by our joint work with Alexander Kulikov. So for depth equal to, first I will explain the result for depth equal to. We obtained something like that. So here I first write it in terms of 2/3 plus 1/57 for the reason that I would like to see that it is greater than 2/3. So 13/19 is greater than 2/3. This is kind of important because we will, one of the reasons is we will see for depth 3 that it can be done with 2/3 and to the 2/3. Okay, then it was later improved to this one, and then later in groups and others, in the paper by groups and others, to this one but for a special case, for circuits with read once gate on the bottom. So on the bottom, each majority receives different inputs. So you cannot input the same variable twice to the same majority. This is the restriction. This is a bit annoying, but we do not know how to extend this to general case. On the other hand, with respect to our comparison to sorting networks, in sorting networks, if you start with a sorting network and you get a circuit for majority from the sorting network, you will have this property. So it applies to circuits that we obtain from sorting network. As for the upper bounds, there is a non-trivial upper bound. It's like this one. So there is a couple of constructions actually for that, and also for arbitrary threshold. So if I mean the following. So if, okay, in the results here, it is not really important whether we allow the threshold in the majority be something else compared to n/2, because all of these results are up to the constant. All of these, sorry, I am talking about lower bounds. Yeah, still kind of, actually, the first two results are up to the constant, and the third, it doesn't really matter. So as far as I remember, actually, I think it doesn't matter in the third result as well. So there you can allow any threshold for the majority gates, because you can always, if you want to simulate some threshold other than n/2, you can add more variables and substitute them by zeros and ones, but that's it. Here we want, so there are results that in this result constant matters, and it turns out that the results are different for two different settings. If you do not allow other threshold, then the best upper bound we know is n-2. If we do allow that, that's at most 2n/3. Okay. So for depth greater than 2, what do we know? For depth 3, there is an upper bound, which is n to the 2/3. For larger depth, there is a lower bound that is actually a straightforward generalization of our results from the previous slide. It looks like that. So what it doesn't look nice, but if you, for large depth, for large D, you can imagine, for example, that 12 is not there, and then it is just 2 over D in the exponent. For small depth D, you can imagine that 12 is 13, and then it is, okay, it is roughly 2 over D plus 1, right, for small depth. Roughly something like that. It is not precise. I also would like to mention a related research direction here. There was a very nice paper, just to mention it, so you know that something like that exists. There was a very nice paper in 2022 where it was, so the model is quite similar. We compute majority as a function applied to some other functions, and the fan-in is bounded. So for H, the fan-in is bounded. So the number of variables is bounded by T. For G functions, the number of variables is bounded by K. And this is very similar to our setting, but now in our setting, the functions must be majority function, and here they can be arbitrary. And then there is a lower bound. We prove the lower bound actually. T must be at least n over k times log k. Note that without log k, this lower bound is obvious because you want your function to be able to read all inputs. So if I remove log k, then it is obvious. On the other hand, this lower bound is tight because what you can do, you can actually compute this with this t. What you can do for each you can break your inputs in blocks of size k, and on each k you can compute the number of ones in binary. And when you do it, your h, so the function h knows you can compute the number of ones in total in the whole array in binary. It doesn't matter in binary, not binary, so just compute the whole number. So if you just, for each k, you introduce log k gates, for each block you introduce log k gates, that just compute the number of each, so these gates together compute the number of ones in binary there. Okay, so that's what I wanted to tell you about a related model of computing majority, and these are our results. So let's get back to our model. So we want a sorting network with k sorters, and the depth is d, and we want to find the minimal k. These are the results. So first, lemmas are simple results. Theorems are not that simple results. So for d up to 2, we can do nothing non-trivial. K must be equal to n. Of course, you can always compute anything. So you can always sort with k equals n because just one gate sorts, one comparator sorts your whole array. For d less or equal than 2, for d1 and 2, you cannot do better. For d equals 3, you can do something non-trivial. You can do roughly k equals n over 2. And this is tight, so you cannot do anything better. So k is still linear. For d equals 3, for d equals 4, we can finally get to something sublinear. K must be equal to n to the 2/3 up to a constant. And also let me note that all of these things are actually tells us that there are no recursive constructions. There are recursive constructions. They do not give good results. No recursive constructions. So this k is not small enough to allow for recursive construction, yet you eventually log square depth. And for arbitrary depth, we have something like that. Again, if you ignore some details, like there is a ceiling operation and the rounding up operation, the exponent, if you ignore it, then it's just d over 2 in the 2 over d, sorry, in the exponent. So it is similar to what we had before, but I will show it on the next slide. So here is the comparison of what we know about majority and sorting networks. What I would like you, so these are all the results I mentioned just on one slide. What I would like to stress here is that there is this thing. So for computation of majority, the depth, so the k becomes sublinear for depth equal 3. For sorting it only happens for depth equal 4. There is this nice difference, so nice, and it gets to the same value actually. At least as far as we know, because for the majorities, we do not know whether this bound is tight. But as far as we can see now, it is similar. It's n to the 2/3, but depth differs by 1. Okay, and for large depth, this is roughly n to the 2 over d, and this is also roughly n to the 2 over d. Okay, so I have explained the result. Then at this point, I would like to switch to discussing proofs. We have plenty of time. Oh, no, sorry about that. It's not really true. So for read one's majorities, we actually have slightly better bounds here, but it doesn't really matter. So I will just skip this, I guess. Okay, before we proceed to the proof, I will need some notation that I will use during in my proof. So this is a sort of case sorting network, and we already know what the layers are. So in this picture, there is layer one, first layer, second layer, and third layer. Also, there are some arrays. And I would like to call these arrays. So to associate with arrays after each step and before each step to the corresponding layers. For example, this array is an array before second layer of comparators, and this one is after second layer of comparators. And I can do it for each layer. This layer here is also a layer. So this is an array before the third layer of comparators. So there is a dual notation. So for each layer, there are two ways to tell what this layer is. But I would like to have both of them for convenience. Also, all entries of all layers, all arrays, I will call by cells. So they are all cells, not just these four, but all of them. Okay, so this is the notation. And okay, now I would like to proceed to the proof. And I would like to structure this part in the following way. So I will give you some ideas of what we use in the proof. And then we will see what these ideas imply. So we will see how they help us to solve things. And the first idea, the main idea.
Volodya, before you start to explain the proof, in the third layer, do you need the red sorter?
No, you don't. No,
okay.
you can remove it. Yeah, you're absolutely right. If you want, we can skip to this part right away, because you are right. This picture actually is an example for d equals 4 and k equals n over 2. I will eventually get there, but we can do it right away if you want.
No. I just wanted to check.
I see that you already solved it. Okay. Okay. So the first idea, I will concentrate on ideas for lower bound. The first idea is the notion of excess. So let's consider a sorted network. It's on the picture. Let's consider an input, some fixed input of zeros and ones. We have 0-1 principle, so it's enough to consider zeros and ones. And also for lower bound, it is even more obvious. So we just consider zeros and ones. Okay, we have an access to some cell if this cell contains 0, and cell is any cell in this picture, right? And also we can switch some input from 0 to 1, and the cell will switch from 0 to 1. So we have an access to the cell if we can actually. So okay, you can imagine it in the following way. So you are here. So you are here on the right. So sorry, you are here. You are here, and you can control inputs. So you can change them from zeros to ones. You can switch on the inputs. You have access to some cell. You can imagine that these are light bulbs, right? So you can switch the light on in some input, and then something will happen in the next arrays, right? So when the next levels on the network, something will also switch from 0 to 1. So you have access to some cell. If it is currently switched off, if it is 0, but you can switch it on just by switching one input variable. So that's and to give you an example, I actually have an access to this particular cell. So this is the cell to which I have an access. I can switch it to 1 just right away. How do I do that? I have a picture for that. For example, like this. So if I switch this thing to 0, from 0 to 1, then in this array, I have now 2 ones, and after this layer it will be sorted, and this thing will switch to 1, right? Then I will have to look at this part. It already contains 3 ones, and it is here. And if I switch the last 0 to 1, then this thing will switch from 0 to 1. This is the notion of access. So we have access to this particular cell, and to give you a full picture, that's what we have an access to here. So in this particular example, I just marked all of the cells to which we have access. There are two observations I would like to make here. The first one is on the left. So note that you have access to all inputs, all 0 inputs, because you can switch them to 1. Another observation is on the right. Note that if your sorting network is sorting correctly, then you can have access only to one cell on the out, because this thing should be sorted, and if you switch something from 0 to 1, it should be still sorted. So this 0 must switch to 1, and this is the only way. And this is an important thing for us. Okay, and related to, so there is an important property of an access that we would like to use, and access is stable. The idea is the following. So if you have access to some cell and you do something, you switch from some input from 0 to 1 in such a way that you do not switch. Oh, okay, we have an access to this cell. If we switch some input from 0 to 1 in such a way that this cell is still 0, then we still have access to it. So basically, there are two things. So if we switch some input from 0 to 1, there are two possible outcomes. Either this particular cell switches to 1, or it doesn't, and then we still have an access to it. That's what I would like to say. Let me see if I have pictures for that. No, I do not have it. I can. So it is not hard to prove. You can. The easiest way probably is to prove it by induction on the depth of the cell, because for inputs it's kind of obvious. If you switch some other input to 1, you still can switch your current input, your favorite input to 1. And then for the step of induction for this particular cell, you can observe that you can. Okay, no.
But why we just don't switch the same input, and then it will get, by monotonicity, it will get 1.
You are right. Yeah, you can do that. Yeah. Yeah, you're absolutely right. Yeah, you can explain it this way. Yeah. But just using monotonicity. So if we have access to this thing, we have access from. So there is some input that gives us this access. It was this one, and since it's still 0, we can still switch with an input to 1, and then you are right then that each cell is monotone, and then this must switch to 1, right? So yeah, because otherwise, yeah. So how exactly? So Sasha, how exactly do you finish this?
Imagine that some change will give 1,
right?
Other change doesn't give 1. But if we use them both, we should have 1, because even one of them is enough. And so we assume that since the other doesn't give 1, then we
I
can
agree.
change them in any order.
It's simpler. Yeah. You're right. It's easier. Yeah. Okay, good. So we have this lemma. Access is stable. Great. So now, now we can actually use this notion to prove some lower bound. And I will start with the lower bound for arbitrary depth. So for the arbitrary n, k, and d, we have this lower bound. And okay, I can prove it now. And how I will prove it? I will assume by contradiction that this inequality. Okay, first there are two things. For convenience, I will assume that d is even, just to make the proof a bit cleaner. And then if d is even, then this is just n over 2 to d over 2, right? 2 over d, sorry. 2 over d. I can just remove this rounding up operation, and it's just 2 over d. And now by contradiction, I assume that k is less than k to the d over 2 is less than n over 2. That's what I need. Okay, what do we do now? We consider 0 input. You can see that zeros are on. So here we have just zeros. We consider the output is also obviously 0. We consider some cell in the middle. So this is some cell in the middle. So there are d over 2 layers on the left and d over 2 layers on the right. And we consider some cell to which we actually have an access. So we have access to some cell on the middle. Consider one that we have access. What we do now, we can observe that this cell is connected to at most k to the d over 2 inputs. do I need to be more to give you more details here, or is it clear what I mean by it is connected to these many inputs?
Just because each time going left, you connect with k inputs. So
right. Yeah, right.
Times,
yeah. My question is basically, is it clear what connected means? If it is clear, I do not. It's great. Yeah, because sometimes I need to explain that there is a graph underlying this thing, and there is you can. It means connected in this graph, and okay. But if you understand, this is great. Do not
something which theoretically could influence, even if it just in
right. This is again informal, but sometimes I need to do it formally. But I see that I do not need to explain it formally, so it's great. It's the same here.
That cell computes a function of k to the d over 2 inputs.
Yeah, you can put it this way. Yeah. And the same with outputs, but you cannot put it this way now, right? So it is connected to at most this many outputs through comparators. So by connected, you mean that if cell is input to some comparator, then it connected to all of its outputs, and we just expanded to the right and to the left. So and k to the d over 2 is less than n over 2. So we know that both of these sets are of size at most n over 2. Less than n over 2. Good. Now what we do next? We start switching some input from zeros to ones. And more specifically, this is a blue color. I hope it is visible. And more specifically, I will switch some input from 0 to 1 that is not in my set, that is not connected to my cell. So this is still 0. However, this is 1. So since the output is in sorted area that is on the input, this is 1. And then I repeat it. So I take the next cell that is not connected to my favorite cell, and this is 1. Okay. One observation here. You can see that somehow, okay, obviously I switch. So on the right, if I switch something from 0 to 1 on the left, on the right, the top things will switch from 0 to 1, right? So it should switch from 0 to 1 from top to bottom. But somehow it turns out that these things on my picture are in my set, in the set of things that are connected to my 0. This is not a coincidence. So this is what should be the case, right? Because what I can do instead, I have access to this thing. I should be able to switch something to 1 here in such a way that this switches to 1, and then, but on the output, the same thing switches to 1, the same top thing. So actually,
so you assume that it was not yet switched to 1, the middle cell.
Yeah, of course. Again, so when I switch something from 0 to 1, so to ones on the left, I pick the inputs that are not connected to my favorite cell.
Yeah. Sorry.
Yeah. So what I'm saying now is that the things that are switched from 0 to 1 on the right, they are actually connected to my favorite cell, because my favorite cell can affect them as well. I can switch. Instead of switching something else, I can switch my favorite cell from 0 to 1, and then the output will be switched from 0 to 1. They can be affected. Mm-hmm. Does it make sense? Okay, let me go to the...
Volodya, this is not clear, because there might be that other cells will produce 1. And
we can make 1 in the last row by switching also some input inside the zone connected to middle 0, because we can switch any 1, we can switch any 0 to 1, and this will increase the number of ones on the right, so it will
okay,
and then
yeah, what is important here is that we should look at this middle layer. If I switch this thing from 0 to 1, okay, let me use another card. If I switch this thing from 0 to 1, then on the middle layer, only my favorite cell will switch from 0 to 1.
This is
and nothing else will change
everywhere.
Yeah.
And why we know that this is the only one?
Because on every layer we have a permutation. It's a sorting network.
It's the same number of ones on each layer.
Same.
Ah, I see. Sorry. I see.
Okay, yeah. So now I hope it is clear that all of these things that switches from 0 to 1 on the right must be connected to our favorite cell. And now we are kind of done because, okay, let me make the next step. Now I switch this thing. Okay, let me switch to purple, back to purple. I switch this one from 0 to 1, and then this switches from 0 to 1. And on the next step, I get a contradiction because I switch the next one, and now I have run out of this area. And the reason is that outside of the area on the left, there are at least n/2 cells, and inside of an area on the right, there are less than n/2 cells. So there are just, I can switch all of them from 0 to 1 on the left, and eventually I will get out of my area of this area on the right. That's it. Does it make sense?
It seems.
No, I didn't get it. Sasha, have you got it? Okay.
I think yes, but,
yeah.
But what part is not clear? It's even I can understand.
I mean the last part of the proof.
No, so we have we're switching from 0 to 1. From on the left, the elements which do not influence this middle zero.
Okay.
And it's a lot of them.
Yes.
We proved already. So each of them should increase one element in the zone connected to the middle cell.
And then
there are only few of them.
And at the last step, we switch the variable which provides access to this zero in the middle.
No, we just see that there are more variables on the left, that variables on the right, and still switching each of them should switch each of left variables should switch each of right variables.
Okay.
And there is not enough of them.
Okay.
Yeah.
But why do we need this middle cell?
Because
we only
define
needed
this.
Yeah, so we define the set. So the middle cell, because we can consider this middle cell, we can say that, okay, there is a set of inputs that are connected to it on the left, there is a set of inputs that are outputs that are connected to it on the right, and then after that we switch all other inputs. So all inputs in the set A that I denoted by A now. That's what we do. So we have access to this cell in the middle. We do not actually use it. We never use it in the end. So we use access to other cells instead.
So why switching something in A should affect something in B exactly? Like
how it can happen? So because actually, so there are many cells here on this layer that are also connected to some cells here. So if you change some. So your question is how is it possible, or why this will happen?
No. Why? I mean, so I understand
why
that, like on the right side, the size of B should be at least size of like n minus A, because like if we change something in this like 0 point on the left, right? Then it should affect and this. Right,
so what? Yeah. I guess I think I get the question. So we switched this thing from 0 to 1 on the left, and this thing switched from 0 to 1 on the right. But also, instead of that, what I could do, I could say, okay, let me switch this cell in from 0 to 1.
Okay, right.
And then this one will switch, and then this one should switch, and they should be connected. And this is a contradiction.
Yeah. Okay. I see.
So basically, I have too much freedom on the left compared to the access to the access on the output through my favorite cell in the middle. Okay, is it clear?
More clear than in the beginning, right?
Okay, more clear. Okay, we achieved something. Okay, let's move on then. Now, I would like to switch to discussion of constant depth. And then, okay, what happens? What we would like to prove lower bounds. What we can do now? Okay, let's do the following. So consider network with parameters A, K, and D, and what are the reasons this network might be incorrect? So what are our possible reasons? And there is an obvious reason. If on some input we have access to two cells on the so after the last layer in two cells in the output, then the network is incorrect, right? I have mentioned this before, so you cannot have access to two different cells in the output. So if you have that, this is a problem. And let me check. I don't have pictures for that, but as an obvious corollary, K for D equals 1, K must be equal to M, because okay, this is our array, this is another array, and there is the middle of array of there are some comparators in between. So this is the input, this is an output. If there are two comparators there, this one and this one, then I obviously have access to two different cells in the output, because I can switch something from 0 to 1 in this comparator and get access to some cell here, and I can switch from 0 to 1 in this comparator and get some access to some cell in the output of the second comparator. So I have access to two cells. This is an obvious observation. I'm just I do not need all previous information for this observation. I just put it in this terminology. Is this clear? Okay, good. Then let's move on to D equals 2 for the depth equal 2, and for that we would like to slightly improve our condition. So our previous sufficient condition for the cell to not work correctly was related to cells on the output. We would like to move to the previous layers, and what we can do is the following: if on some input we have access to two cells before the last layer, on this picture it's here, not just two cells, but two cells that go to different comparators, then the network is incorrect. So if I have access on this picture to two different cells that go to two cells that go to different comparators, this one goes in blue and this one goes in red, then I have this network cannot work correctly, because this would mean that I have access to two cells on the output layer, right? Because of this I will have access to one of these things, and because of this one I will have access to one of these things. I do not know which one, but this is obviously an access to two different cells on the output. Okay, hope the condition is clear. But then you can actually from that get that K is equal to N for D equals 2. And actually, so you can observe that this is nothing else than a well-known problem for math. I do not know, extracurricular math classes for high school students. There is a well-known problem that if we have a store and the store sells some vases, and we know that in the store there are vases of different color and there are vases of different shapes, then there is a couple of vases that differ both in color and in shape. And this is exactly what we get here, because, okay, imagine that K is less than N. Then the vases are here in the middle. So imagine we have this open network. The vases are here in the middle. And here we have color. And here we have shape. So you know that you have two vases that are of different color and both of different color and then shape. I can find you an example, I guess. Maybe this one and this one. And then this gives me the following. I can actually get access to these two cells because they come from different comparators. So I can, for example, here in the red comparator, I have switch set it to 0 and 0, and then I have access to this cell. In the blue comparator, what I can do, I can say set this to 0, 1, 0, 0. So 1, 0, 0, 0, I have access to this cell now. And they go to different comparators. So they will give me access to different cells on the output.
Just for blue one, you need 2 ones, I guess, no?
Why? I sort from bottom to top. On the output, I want to have 0, 0, 0, 0, 0.
Yeah, but just to get 1 in the third from the bottom, you need 3 1.
No, but so I'm using this one in the red color. So it will have 0, 1, 0, 0, 0. That's exactly what I need, right? So
yeah, but you need already 2 to make the 3. But okay, it doesn't matter really. But
no, why do I need it to make it 3? So
because
I
it's
think
third from the bottom, so you need 3 ones to get 1 there.
3 zeros.
no, but ones are from the top. One goes from the top. So I start from bottom to top. For the reason that is not clear.
Sorry.
Yeah. So in the output, I want something like that.
Yeah.
Okay, so this part, I hope, if it is not clear, please let me know, because I will move on to other things now. If it is clear, then let's move on to the next idea. To do something for larger depth, we need another idea. And we will need a notion of a growing branch. A growing branch is a sequence of inputs, x1 and so on, xp. xp is the length of the branch. And in such a, so the sequence is the following. Each next xi plus 1 is obtained from xy by changing one coordinate from 0 to 1. That's it. So let me give you maybe an example. So for example, we can have x1 can be something like that, x2 can be something like that, x3 can be something like that, and so on. So each time I switch something from 0 to 1.
So it's just chain, right?
Yeah, it's a dense chain in Boolean cube. Yeah. Okay. So and then using this notion, we can actually prove the following lemma that we will unfortunately have to read. So if you consider a certain network with n, k, and d, and if we assume that there is a growing branch, x1 and so on, xk, so the length of the branch is k, the same as the size of the comparator, such that for each xi, we have access to at least 2 cells before the last layer. So note that on the previous condition, we had, so for depth equal to, it was enough for us to have 2 cells before the last layer to go to different comparators. Now we want to something more advanced. We want to have 2 cells, not necessarily going to different comparators, but we want them have access to them for each for each input in our chain, in our growing branch. We want to have access to at least 2 cells before the last layer. That's the condition, and then the network is incorrect. Maybe I should move to a picture, because I have the slide where I have the same lemma written down here, so you can read it. You can still read it, and I have a picture because we are going to prove it now. So I have a big picture for the proof.
So the starting point of branch is not necessarily 0, or should be, or have to be 0.
Exactly, it's not necessarily 0. Yeah. The starting point can be any input. Yeah. Okay.
And k is arity, right?
Exactly. It's the arity of a comparator.
Okay.
Okay, let's move on to the proof. The only thing, so I will give you a proof. The only thing is, for convenience, I will assume that instead of at least here, I will have exactly. It just will make the explanation of the proof a bit more convenient, so we do not have to worry about something. So if I have exactly access to exactly 2 cells before the last layer, then the network is incorrect. That's what I will prove. Okay, let me prove it. So here on this picture, you have a network. This is the last layer. As you can see, it is written down here. I have an input x1 currently. I have access to 2 cells. First of all, if they go to comparators of different colors, if they are inputted next to the comparators of different comparators, then we are done, right? So if the colors here are not the same, then we are done, because then we have access to 2 different cell modalities. We have 1. So from now on, I will assume that I have access to 2 cells, two cells, but they go to the same comparator, because this is the hard case. What I do next? I switch my input x1 to x2. So I switch to the input x2. What does it mean? I switch some input variable from 0 to 1. What happens? I lose access to one of the cells. So I had access to at least to exactly 2 cells on the before the on this layer, on this level, and I lose an access to one of them because some 0 will switch to 1, right? So I have one. It should be one of them. So let's say this one. So this is now 1. But I also know that on input x2, I have access to 2 different cells on before the last layer. So I get an access to the new one. It is important. I also keep an access to this one because access is stable. So even if I switch something, one of the cells I had access to is now 1. So it's not, I don't have access to it anymore, but I have access to the previous, to the other one. And again, if the color of this new cell, I mean, if the comparator, this new cell goes to a different comparator, again, we are done because now we have an input on which we have 2 cells, access to 2 cells that go to different comparators. This gives us 2 cells on the out. So the hard case is that it is the same comparator again. All right. Okay, let's just do this once again. Now I switch to x3. Again, I lose access to one of the cells, this one. I keep access to another one, so we still have it. We still have access to this cell, and this is new. We have access to some new cell. And again, if this new cell is inputted to another comparator, then we are done. If it is the same, we repeat. So I can repeat it k times. If at some point I get access to another comparator, we are done. If it is not, I have access to all of these cells that go to the same comparator, but note that there are k plus 1 of them, because on the first input I got 2 cells, and each next step I get 1 more. I have k steps in total, so it's k plus 1.
Volodya, and
yeah.
why you claim that you lose access to one of the cells when you switch, when you increase I?
All right. So I have access to exactly 2 cells. That's my assumption. So I have said that just to simplify the proof, I have access to exactly 2 cells.
So one of them should be the one that is switched to from 0 to 1 is this one.
Yeah.
Because
so
you don't have access.
So one
to
of the cells must switch from 0 to 1, and we must have access to it, right? So
I see.
Yeah. Yeah. Okay. Hopefully this is kind of clear, and then we can move on to. Oh, I have a corollary. That is kind of important. So it's the same lemma. So if you read it, it's exactly the same. If we have a certain network N, K, and D, assume that we have a growing branch, such that on every input we have access to, and this is the difference. Here we have at least 2 cells before layer D, and here I have at least 2 cells before layer D plus 1 that go to different comparators. Because if I have access to 2 cells before layer D plus 1 that go to different comparators, that give me access to 2 different cells before layer D on the next, after one layer, right? Because cells that go to different comparators give me access to different cells after the comparator. Okay. Somehow, maybe it's not ideal, but somehow I have we can have a short break at this point because we move to depth 3, and we can discuss upper bound if you want before we actually move to lower bound. So this is okay. Let me explain an upper bound to you. So it was so for depth 3, the upper bound is like that, and in the proof I will provide you here, I will assume that n is even, because for odd n, this construction actually doesn't work. But I still already have this construction, so I will explain it for even n. And this is the same picture we had before, and actually it gives the construction. So the idea is the following: on the first, so we break an array into halves. On the first, okay, we actually do the following: we break an input into quarters, into 4 quarters. On the first layer, we sort the upper half and the lower half. On the second layer, we sort these 2 quarters and these 2 quarters together. And on the last layer, we sort the middle. And as Bruno already observed, we do not need this part at all, actually. This is here it is on the picture for uniformity. We actually don't need it. Okay, just to understand that this actually works, I will explain from this example for n equals m. And it's kind of simple. Let's look at the maximum. So let's look at the maximum in the array. Where can it be after the layers? So in the beginning, it can be anywhere, but after the first layer, the maximum can be either here or here, right? Because it should be in that it gets to one of the two comparators. It should be in the top of these two comparators after that. And then if I look at the second layer, then these two things go to the same comparator, right? So maximum is necessarily here, right? So this is, we already sorted the maximum. Let's look at the second largest number. Second largest number can be, it can be here, because okay, it depends on the input, right? So it's, if both of them, largest and the second largest, get in the first comparator, then it is the second largest in the first comparator, or it can be largest in the first comparator, or symmetrically it can be here. The second largest can be in one of these four things. And then note also that on the second layer they go to the same comparator. So the second largest will be here after the second comparator. So this is the second largest. Also, you can note that the picture is symmetric. So it is the same for the minimum and the second minimum. So after the two layers, two largest numbers and two smallest numbers are sorted. So what is left to do is to sort the middle, and that's what we do on the last layer. And this generalizes to arbitrary n, actually. So if you have arbitrary n, you do the same thing, and after two layers, you have the upper quarter to be sorted and the lower quarter to be sorted, and you have to sort the middle on the last layer. So this is an upper bound. Okay. So, okay, now let's move on. I think I will have enough time to discuss depth equals 3, and we will not have enough time for depth 4. Okay, let me remind you. Okay, I probably have to go a couple of slides back. So what do I need? What is the current condition to prove that the network is incorrect? If it is incorrect, if you have a growing branch, such that on every input you have access to at least two cells before the layer d-1, so two layers before the end, and these two cells should go to the different comparators. And now what I will do, I will draw you a picture for d equals 3. And I will give you a combinatorial reformulation. So a reformulation of this setting in terms of puzzles. We will consider the following cube puzzle. And by cubes here, I mean just cubes that kids can play with, right? So colored cubes that you buy in a box and you can build towers of them and so on. That's what we will do. So this is a network of depth 3, and we are interested in this layer that is in the orange, is marked by orange color. So this is two layers before. So we need a growing branch in which we have access to two cells in this layer that go to different comparators. So looking at this layer, I can draw a picture like that on the right. So on arbitrary input, I can draw this picture. So how can I see this stacks of cubes on the right? I look at the outputs of comparators on the first layer, and okay, yeah, maybe let's use the purple one. So I have this output of so I look at the zeros in each output of the first layer, of comparators of the first layer, and this will be the stacks. Stacks are the outputs of comparators to the first layer. You can see them. So this is the stack of this is this one, and this is this one. Where can I see the colors? I can see them on the right. So these are the colors. You can again, you can see that corresponds to the picture on the right. Okay, so now we have this stack of cubes. So what are we able to do? So if we switch something from 0 to 1, that's what happens in our branch, right? So we start with some input x1 and we switch something 0 to 1. If we switch something from 0 to 1, then in one of these stacks here, so for example, if I switch this one to 1, then this one will switch to 1. In terms of stacks, it means that I take this cube, right? So I remove this cube from my tower. Okay, and so what does it mean? It means that on current input, I have access to the cubes on the top of each stack. So I have some stacks of cubes. In one step, in one move, I can take one cube from the top. Okay, I have access to cubes on the top, right? So I have access to them. So what do I want to do? I want to have access on cubes of the top, to cubes of different colors. So I have I can play this game, right? So I have this stack. I can, in each move, I can take one of the cubes from the top. I want to have access. I want to see cubes of different colors on the top, and I want to see it for many steps because I want a branch, right? I hope this is kind of intuitively clear. Let me formalize the puzzle completely. So we can forget about source networks at this point. Just where is this puzzle? You have n cubes. You have a set of n cubes. They are arranged in vertical stacks. Each stack is of size at most k. Why? Because the size of each comparator on the first layer is at most k. So each stack is of size at most k. Each cube has a color. For each color, there are at most k cubes of this color. Why? Because colors correspond to stacks on the second layer. Size of each size corresponds. Color corresponds to comparators on the second layer. So each comparator has at most size of at most k. So you have at most k cubes of this color. So for each color, there are at most k cubes of each color of this color. So in one step, you are allowed to take one cube from the top of the stack. That's it. Our plan. So what do we need to do? We need to show that we can start with this stacks of cubes. We can take cubes in some order, in such a way that we have cubes of different colors for at least k steps in a row. So what we can do? We can start with some set of cubes. We can, before we actually claim our property, we take some cubes from the tops, and then we claim our property, and then we have to maintain it for k consecutive steps. It should be for k consecutive positions. So again, what I tried to explain is that exactly. So if you can do this, this will give us exactly a growing branch of length k, and this will imply that there is no source network with parameter n, k, and d equals 3. That's what I would like to claim. I explained that. So if it is not clear, please let me know. I do not know. So yeah, I think we have time to discuss why is this true. If it is clear, great.
Can you
It's
remind?
difficult to follow, but I guess it's not possible to go to explain.
Okay, it is. I know that it is. Okay, Bruno, yeah.
How many colors?
Oh, you can have as many colors as you want, but you know that in each color there are at most k cubes of the same color. If you have more colors, it's great. The problem is that there are not many colors. If they are all of the same color, you cannot win,
sorry,
right?
sorry. Okay.
Right. Yeah. Okay, so now we have this game. Hopefully, at least the game is clear. We have a theorem that actually cube puzzle is solvable for k less. You can always solve it if k is less than n/2, and as a result, we know that there is this lower bound which is tight and so on. This theorem actually requires some tedious analysis. Instead, what I will explain you is how to win this game for k less or equal to n/3, because this is easy and we can do it. You can do it easily. There is a question. I'm not sure what was the previous slide at that point, but I will try. Is it this one?
Yeah, thank you.
Okay, great, yeah. And please ask questions because, yeah, it might be unclear. Let me just, since I'm showing this slide, let me repeat the game. So we have n cubes. They are arranged into stacks. Each stack is of size k. Imagine k is n/3. Each stack is of size at most n/3. Each color is, let's say that k is n/3. That's what I will use in the proof. Each color has at most n/3 cubes of this color. And in one step, you can take one cube from the top. You want to have cubes of different colors on the top, and you want to have it in k positions in a row. That's it. Okay, let's win this game for k at most n/3. n/3, these are our cubes, these are our stacks. In the worst case, there are 3 of them, but just in the more general case, there are 4 of them. Okay, let me show you how to win this game. What we will do, we will find cubes of different colors in different stacks. There are such cubes. Again, rather amusingly, so this is the same. This is the fact that we exist is the same weight problem. So we know that there are cubes of different colors. We know that there are cubes in different stacks. We can show that there are cubes of different colors in different stacks. It's the same problem on basis. So there are 2 cubes of different colors. First, on the first step, what I will do, I will take all cubes from above. So I will take all cubes that are on top of them. So I will make them to the. So I will move them to the top. Basically, I will take all cubes that are above. Okay. Now I claim my property. So I claim that I have 2 cubes on the top that are of different colors. What I will do next is kind of obvious. I will just take all cubes from different columns. So okay, here I just claimed all that I have my property. Next step is I will take all cubes that are here. And there are at least n/3 of them. Because this column contains at most n/3 cubes originally. This column contained at most n/3 cubes originally. There are at least n/3 cubes left there in our column. So if I take all of them, I get at least this many steps where I have different cubes of different colors on the tops. Great. Okay, does it make sense?
Yeah.
Okay, what I can do now, I can for depth 4, actually the upper bound was kind of known. It was not known explicitly, it was not stated explicitly, but if you just look at column sort of Layton, then you can, it is a recursive way to sort, and then you can observe that it's basically just sorting network of depth 4 with k equals n to the 2/3. So it was known. Okay, I have 2 minutes, right? Or do I? So should I stop here and take questions, or should I use 2 minutes to explain something that you will not understand?
I'm afraid that it's difficult to explain in 2 minutes this theorem.
Okay, yeah. Okay, let me explain you, let me tell you that something complicated is going on there. So what we do for depth 4, we unfortunately do not move to, we had a condition in terms of this level for depth equals 3. We cannot move it further, so we do not know how to move it further. Instead, we consider a more complicated cubes game with 2 sets of cubes that are kind of connected to each other. So you take some cubes from here, and as a result, you take some cubes from here as well. So we are connected. And then we explain how to win this game. And so what? Yeah, I explained this game here, but we will skip it. What here? Yeah, so. And here is the idea of how to solve this game. It is a randomized construction, but it doesn't really matter now. I have the slide with results that are again stated here. That's basically it. Please ask questions. Okay.
So for d equals 4, the theorem is much better than the lemma. The general lemma for arbitrary.
Yes, you are right. Yeah, exactly. Yeah. And this is true for d equals 3 as well. Yeah.
No, yeah. And about d equals 5, you have no idea. Is it possible?
Yeah, I think we have no idea. Yeah, I think we have no idea. As far as I remember, it is not. I do not think it's not obvious how to even get an obvious because usually, for example, with Boolean circuits, you can get something obvious. You can say, okay, let's say that k is really small, and then let's collapse 2 layers into 1 because then with k squared instead of k. Here it's not clear how to do it because comparators are so interconnected that you cannot collapse the two layers of comparators of arity k into one layer of arity k plus k squared, because they are really all they can be really all interconnected. And yeah. So no, I do not think, no, okay, there is this lower bound, of course, but I do not know how to improve it.
Okay, thank you.
Thanks.
Hey, thank you.
Thank you.
Thank you.
Thank you for your talk.
Thank you.